Hi, this is Patrick from STH. Today we're going to do a follow-up video to our previous EPYC and Broadwell architecture discussion, and we're going to show what you need to know about dual-socket AMD EPYC architecture versus the new Intel Xeon Scalable architecture. We have a lot to cover today. After watching this video, you'll be able to articulate how the new AMD EPYC and new Intel Xeon Scalable processor architectures differ from each other, but also from the outgoing Intel Xeon E5 generations. You'll be able to explain how the different architectures impact intra and inter-socket communication. You'll be able to show a very narrow use case where Intel actually has more effective PCIe lanes in a two-socket configuration than AMD EPYC. You'll understand why AMD EPYC systems will effectively have less than 128 PCIe lanes available to users. And finally, you'll be able to observe why the AMD EPYC PCIe model is more flexible than Intel. That's a lot to cover, so let's get started. Before we talk about dual socket systems, we wanted to talk about single socket very briefly. Here, AMD EPYC has 2 terabytes of memory, 128 PCIe lanes, and a ton of cores, as well as single socket specific SKUs that provide a discount over the dual socket counterparts. In short, AMD has a killer platform in the one-socket market, and Intel really needs to figure out an answer. I wanted to start with the basic building block of the AMD Zen architecture chips, which is the CPU complex, or a CCX, which has 4 cores. It also has level 3 cache and the ability for each of the cores to talk to each other in a very low latency fashion. 2 of these CCX complexes go on each silicon die, and then those are packaged up in 4 dies per EPYC package, and that's how you get up to 32 cores. We're going to run through several of AMD's slides just to explain why we're doing what we're doing, but the Infinity Fabric is a interconnect that allows AMD to stitch together smaller pieces of silicon and achieve a larger total system. So one of the first slides that AMD gave us, they show that each of the up to 8 core die per package can address 2 channels of DDR4 memory and up to 2 DIMMs per channel. Each die is connected on an on-package Infinity Fabric link. Then those Infinity Fabric links also have the ability to link between packages, and each die also has the PCIe subsystem. Finally, AMD put together a picture that ties everything from memory to the cores, as well as each socket to socket connectivity. It's missing one part, which is the PCIe lanes. So in our depiction, we're going to fill in some of those blanks. Here's our base depiction of a 2-socket AMD EPYC server. You can see that each of the silicon dies is connected to each of the other silicon die on a AMD EPYC package using Infinity Fabric. You can then see that each die is made up of 2 CCX complexes, which each have 4 cores. And then to connect the 2 sockets, you have each die can communicate to its respective die on the other package. So therefore, we have die 0 on the first package can talk to die 0 on the second package. Likewise, there's an Infinity Fabric link directly from die 1 to die 1, die 2 to die 2, die 3 to die 3. Because AMD has both on-package and socket-to-socket Infinity Fabric connections, one can actually take multiple paths to get from socket to socket. So for example, if die 0 on package 1 needs to talk to die 3 on package 2, it can either go from die 0 to die 0 and then to die 3, or it can go die 0 to die 3 and then over to die 3. That's part of what makes AMD Infinity Fabric awesome. It can actually route data through multiple paths. Now, most of the tech talks that you'll hear and one of the slides that we saw earlier depict memory hanging off of this Infinity Fabric. And what you'll see is that each of these dies, they each have 2 memory channels. And so you can then trace the Infinity Fabric. So if a level 3 cache or level 2 cache needs some data out of RAM, you can traverse the appropriate Infinity Fabric and go get that data, and you can trace how that would work if there's a 1-hop or a 2-hop to get there. Alternatively, with pneumaware applications, if the best case, you would have any data that you need residing in the memory that is directly connected to the die, because that's going to give you best performance and lowest latency. The one case that we don't hear that much about, but it's also very important when understanding the architecture, is what happens when we look at PCIe devices as well. So here we have 8 GPUs. You wouldn't actually have this in an EPYC system because you need some of the PCIe lanes for devices like SATA devices, BMCs, and what have you. And you probably also want to have some network controllers, but this is just a depiction. So let's think about what happens if you have GPU to GPU communication in a dual EPYC system. This is going to be a little bit different from how Intel will handle GPU to GPU transfers on the same socket. So for example, if this GPU on die 0 needs to talk to the GPU on die 3, that data is going to have to go over an Infinity Fabric link. Likewise, if the GPU off of die 0 needs to access memory that's sitting off of die 3, it's also going to have to go over the Infinity Fabric link. In a storage server, you can think of this also as if you had a bunch of NVMe devices and you had a NIC sitting off of a socket. Those NVMe devices may have to traverse Infinity Fabric with their data before the data is pushed out onto the network. On a relative scale, the on-package Infinity Fabric adds, say, on order of tens of nanoseconds. So in storage, it's not a huge deal, but the latency is there. And the other impact is that that data flowing over the Infinity Fabric means that there is less available fabric bandwidth for doing memory-to-memory transfers while you're doing PCIe device transfers across the package or from socket to socket. That makes sense in this architecture and is one of the awesome capabilities that AMD has, which allows them to keep manufacturing costs low and still get decent performance out of the architecture. You can see this is a picture of the 28-core die, and we also have depicted the Intel Mesh Interconnect, which is a fancy way of saying that the different cores and components of the die are arranged in a row and column infrastructure, and that there are interconnects that traverse these rows and columns. These interconnects dictate how quickly a given core can access memory, for example, or PCIe to PCIe transfer can happen. So this new mesh interconnect is actually a big deal. So let's take a look at what that impact is. One of the first differences that we wanted to highlight is PCIe. So in the older Broadwell generation, which is Intel Xeon E5 V4, what you'll see is that the PCIe lanes all sat off of one of the ring buses. And as a result, when you had PCIe to PCIe transfers or PCIe to core transfers, an example of what would happen is you'd have a GPU, you'd have to hit the PCIe hub, you then go into the ring structure across the bridge, you may have to traverse a good portion of the ring again, and to end up either at a core or a memory controller. On Skylake, it's a bit different because now, if you're a core, you can, for example, traverse a single wire and get to DDR4 controllers. You can go through another series of interconnects and get to the PCIe But at the same token, these are not the same latency as having to go and traverse this entire ring structure. Another major architectural difference is that you'll see that this has one hop and one stop, whereas there's a PCIe stop here, another one here, there's a PCIe stop at the end, and then there's this on-package PCIe by 16 stop that we'll get to in a little bit. Here's an example of a memory access where a core from one side of the old ring structure would have to traverse several hops on the first ring, go across the bridge, traverse more hops, and then finally to a memory controller. Whereas in the new Skylake mesh architecture, it can just continue on using the standard mesh structures that are there. Essentially, Intel had to go to a structure like this because while the ring structure made a lot of sense when you had, say, 8 or 12 cores to a die, as they started scaling it to 24 cores and beyond, this became a major limiting factor, whereas the new mesh architecture is expected to scale beyond 28 cores. In essence, what we have is Intel with a large monolithic die versus AMD, which is using smaller pieces of silicon with up to 8 cores each, and then an on-package interconnect. From a performance perspective, Intel has a higher performance solution since the silicon interconnects are very fast. AMD has a significantly less expensive solution to manufacture. And so there are two different methodologies towards achieving a high core count. Now looking at the interconnect, the new generation of interconnect is called the EPYC on the Intel side, and this is equivalent to, if you remember those arrows that we had on the AMD EPYC, where you would see the cross-socket Infinity Fabric links. On the Intel side, you have EPYC links. And there are 3 EPYC links possible on a Intel Xeon Scalable die. There's 2 on this hop and 1 on this hop. And if you have these lower end processors, such as the lower end gold, silver, and bronze processors, are only capable of either 2 socket configurations, or some of the gold ones are capable of 3 or 4 socket configurations, and that's because they're able to use EPYC links, however not the full 3 that the higher end gold and platinum series can use. If all 3 EPYC links are enabled, Intel's quad socket solution actually has a EPYC infrastructure that looks very similar to this, just at a socket level. Moving on to a similar build that we did on the AMD EPYC side, what we wanted to look at quickly was the memory controller. So here, Intel only has 2 memory controllers on a die. Each one can accept up to 3 DDR4 lanes, and each DDR4 lane can have up to 2 DIMMs per channel, and so you get 6 DDR4 lanes total per chip, and up to 24 DDR4 DIMMs to connect. Adding on the PCIe devices, we again are using the GPUs, and we have a couple of PCIe add-in cards that are network controllers. If you hear Intel discuss 48 PCIe lanes per CPU die, this is how they're getting it. They have 3 main stops on the Skylake die, and those 3 stops allow them to have 6x16 connections, which gives you 3x16 is 48. While we like the AMD EPYC flexibility, Intel's platform really doesn't stop at PCIe lanes. It goes a little bit further. So what you'll see is a DMI by 4, so that's a PCIe 3x4 PCH hub. And in this generation, the PCH can have up to 14 SATA devices. So we have SATA SSDs here. Realistically, due to bandwidth constraints, you probably want to have only a few SATA drives, or you want to have SATA hard drives, but you still get those for only 4 PCIe lanes. On the other hand, you get 10 gig networking, and there are some things that you need in a server, such as a BMC, which also will sit off of PCIe. Usually put these onto lower performance PCIe lanes. So in this generation, you can hang your BMC off your PCH PCIe lanes, and therefore you can use 4 lanes on the die, but actually get a lot of connectivity. Flipping over to the AMD side, you'll see that each EPYC die has a series of PCIe lanes. Some of them are used for Infinity Fabric, which are these green ones, but this depiction down here is actually SATA lanes. So if you want to use SATA, you have to actually take PCIe lanes out of your 128 PCIe lane pool in a dual socket AMD EPYC configuration and reconfigure them for SATA usage or for your BMC. There's a number of uses. Intel has other features. They can support up to 4 10 gigabit Ethernet links. They also have various levels of quick assist, but enabling that higher level of feature also will mean attaching the PCH to additional PCIe lanes to get bandwidth. We haven't seen any vendors do this yet, but it is possible to actually use more than one PCH per platform. So for example, if you wanted to have a storage server where you wanted to have boot drives plus 24 hard drives, you can actually do that by adding another PCH if you really wanted to. Now, there's one part of the die that you'll notice that we have excluded from discussion thus far, but we wanted to show you now, which is this on-package PCIe 16. If you look at the Intel SKU list, and we have a list of that on STH, you'll see that there are a number of SKUs with a F at the end. So for example, the 6142F, which is a gold level processor. The F denotes a onboard fabric. That fabric is Omni-Path, and you can think of Omni-Path similar to an InfiniBand interface, so you get RDMA transfers. But from an architectural standpoint, there is one major difference. On the high-end SKUs that actually have fabric, there's an extra PCIe by 16 lane or hub that's being used. It's a different controller, so another stop on the mesh interconnect. But it also changes our count. And the reason for that is that we now have not 1, 2, 3, but now a 4th PCI by 16 hop. And that means that we actually have 64 PCIe lanes per die. So in a dual socket configuration, you actually have 64 by 2, so that's 128 PCIe lanes. And remember, the PCH is providing a bunch of functionality beyond that. Now, Intel doesn't tout 128 lanes because, number one, not all of their CPUs have this. Number two, Omni-Path is only going to be used for a select series of users. However, they actually can scale up to 128 lanes, so their design was up for 128 lanes, but they just have 48 lanes that are potentially available to the vast majority of users. Before we move on, the other thing to note here is that the Omni-Path is actually a 100 gigabit per second RDMA network link and only cost about $155 premium to a standard SKU. That's extremely powerful if you use InfiniBand or InfiniBand-like fabrics, because your alternative is to use a Mellanox InfiniBand card, and at 100 gigabits per second, you're probably spending on the order of $1,000 to $1,200 for a NIC. And that's part of Intel's big marketing push on this, which is that you save about $1,000 per controller by going with Omni-Path over Mellanox fabric. So now that we have the full Intel view, let's go back to EPYC real quick and let's talk a little bit about what happens with their PCIe bifurcation. AMD does have a more flexible PCIe bifurcation since they can go down to by 1. And also they're able to change their PCIe lanes personalities through a BIOS setting. So for example, if you had 8 PCIe lanes attached to, or say assigned as a SATA interface, and instead you wanted to use them as a PCIe interface, system vendors can actually make that a BIOS switch, and so you can reclaim those 8 lanes and convert them from SATA to PCIe. That's not a new technology, but it's something that AMD is using on the EPYC platform. And again, when you do see there's 128 lanes on EPYC, that's not 100% comparable to the Intel lanes for a number of reasons. One is that you're probably still going to use SATA boot devices, so you'll lose, say, 2 or more lanes for SATA. Furthermore, you're going to have BMC and other devices that are kind of platform level devices and servers that have to consume PCIe lanes, and these are things that Intel will push off to the PCH. There's another aspect to this, which is the motherboard wiring and all the wires that go into PCBs. And so, what we're actually seeing in the wild is that EPYC platforms come with a maximum of 96 and a few of them with 112 PCIe lanes exposed. So let's get to a few key takeaways that you can bring to your colleagues. So a couple big ones here. Intel's new Skylake mesh architecture gives them less congestion in terms of PCIe because there are more hops, and therefore they're actually getting more effective bandwidth out of it. AMD EPYC's PCIe solution is far and away something that we prefer. It's more flexible. We really like it. That PCIe solution can actually be set via the BIOS, and similar to what we saw with our Intel Atom C3000 series, among other examples, where you can change a PCIe lane personality from PCIe to SATA, as an example. The other bit is that AMD uses PCIe lanes for what generally would hang off of the DMI and PCH interfaces with Intel. So there's a little difference in terms of how these systems are actually set up and PCIe lanes accounted for. This makes sense. Intel basically has a PCH and DMI interface that has a lot of the lower performance parts that would sit off of a system and has a dedicated bus for that. With AMD, you're still consuming a lot of your high-end PCIe lanes. When you hear that AMD EPYC has 128 PCIe lanes, that's true that the platform has 128 PCIe lanes in a dual socket configuration. However, once you actually get to build a system, because you need to have these PCIe lanes consumed by SATA and BMCs and what have you, you end up with fewer effective lanes than 128, often 96 or 112. Finally, AMD EPYC will actually have a higher chance of going over Infinity Fabric to PCIe, so it needs to be a higher bandwidth. And just to give you a conceptual view of why that's important on the last one, if only one of the 8 pieces of silicon is attached to your memory, you're attached to only about 12.5% of the total system memory without having to go over the fabric on AMD EPYC, versus Intel going over UPI. There's only about half of the system resources that are on the other side of the UPI bus. That's a little bit of a generalization, but that's what we're seeing in some of our latency tests, so it's a good enough conceptual model, I think, to work with. Intel will undoubtedly say that the new Skylake-SP chips have a significantly better memory system than the older Broadwell generation. That's 100% correct. Again, the Skylake-SP cores will have 50% of the total DRAM connected via silicon interconnects, and the other 50% of DRAM will be over the UPI bus, whereas AMD EPYC, you only have 12.5% of the DRAM located and attached to the same piece of silicon as a core may be. At the end of the day, though, AMD EPYC has a much higher memory capacity than Skylake. On the other hand, there are a lot of use cases, especially where software is licensed by Core and that software is very expensive, where the Intel solution with larger, higher performance cores and dies actually makes a lot of sense. There are a lot of opinions online stating that one is clearly better than the other. Those don't make any sense at all. In reality, there are applications where the different architectures perform better than one another, or they have specific features that target applications that make them better. When you take into account pricing along with system level capabilities, we have them both in the lab, and what we can say is that there are use cases where both solutions have merit. We hope you can use this video to start a discussion with your colleagues about the different architectures. Thank you for watching. Take some time to visit the STH main site, check out other videos we have, and subscribe to our YouTube channel.